Hello everyone, I am TanujJhankal. Welcomes you to the new lecture on multi-level inverters. Okay, in this lecture we will study about theory of multi-level inverters. We will see different level of multi and we will also see how their voltage space phasor structures look like. Okay, so let's start with multi-level inverters. Previously, we have discussed that multi-level inverters generate output voltage with stepped waveform by using an array of power semiconductor and capacitor voltage sources. Okay, the commutation of switches permits the addition of voltage of the capacitors, which reaches high voltage at the output terminal, while the power semiconductor devices must withstand only reduced voltages. Okay, now the figure shows one phase lag let pole A of inverter with different number of levels, as which the action of the power semiconductor is represented by an ideal switch of several positions. Now, for two-level inverter, the position of the switch is represented by switching function SA, which can attain any of the two distinct values 0 or 1. The point O is the fictitious point or midpoint of DC link considered to be representation of the pole voltage VAO. Thus, VAO can be minus VDC by 2 or VAO can be VDC by 2 when switch A is at 0 or 1 respectively. For a 3-level inverter, the pole voltage level minus VDC by 2, 0 and VDC by 2 can be attained by corresponding switching function values 0, 1, 2 respectively. In similar way, for 5-level inverter, the pole voltage levels minus VDC by 2, minus VDC by 4, 0, VDC by 4 and VDC by 2 can be attained by switching function values 0, 1, 2, 3, 4 respectively. Okay. Now, in the similar manner, we can generalize for n-level inverters, and the switching function has a range from 0 to n minus 1. Okay, as it is shown in the figure. Now, if we talk about the pole voltage of the inverter, I must say the pole voltage of the inverter defines in the terms of switching functions, and it can be given by the equation VAO, VBO, VCO is equals to VDC by n minus 1, where the other matrix contain SA minus n minus 1 by 2, SB minus n minus 1 by 2, SC minus n minus 1 by 2, where n in the above equation is number of levels of the inverter. Okay. Now let's consider a induction motor with star connected stator is connected to the output terminal of the inverter. The inverter pole voltage can be represented in the terms of phase to motor neutral point voltage and motor neutral to inverter DC link neutral point voltage, or in easy or in mathematical language we can write it as VAO is equals to VAN plus VNO. Okay, and VBO is equals to VBN plus VNO, and VCO is equals to VCN plus VNO. Okay, here the VNO is common mode voltage. Keep it in mind, common mode voltage. It's not common node voltage. So from previous equations, the phase to neutral point voltage can be expressed in the terms of inverter pole voltage, and it means we can represent VAN, VB and VCN in terms of VAO, VBO and VCO. Okay. Similarly, the motor line to line voltage can be written as VAB, VBC, VCA can be written in the form of or in the terms of VAO, VBO and VCO. The inverter pole voltage contains harmonic of third order and its multiple, which are triplet harmonics, and these triplet harmonics are absent in the phase to motor neutral voltage and line to line voltages. Okay, now if you want to see how to calculate VA and VB and VCN, here is the calculation for VA and VBN and VCN using above equations. Now, the inverter voltage space phasor is represented in the terms of three pole voltages, okay, which are VAO, VBO and VCO, and it will be given by Vs equals to VAO plus VBO e to the power minus e to the power j 120 degree plus VCO e to the power j 240 degree and it is represented by Vs. Hence, the inverter voltage space phase, the combined information of all the three phase voltages. The space phasor Vs can also be resolved into two components, okay, which are alpha and beta components, and it can be represented as Vs is equals to Vs alpha plus j Vs beta. It can be done using conventional ABC to alpha beta transformation, okay, by using equation this one, Vs alpha Vs beta is equals to in terms of Va and Vbn and Vcn, and we can also convert back from alpha beta to ABC mode or Va and Vb and Vcn using equation Va and Vb and Vcn is equals to this equation, okay. So using this equation we can convert any three dimension, can't say three dimension, it's a 3-axis to 2-axis system or 2-axis to 3-axis system, okay. Now, as I have mentioned earlier, each pole of two-level inverter can attain two voltage levels, okay, which are VDC by 2 and minus VDC by 2. Therefore, the total number of switching states that a two-level inverter can attain can be 2 to the power 3, which are 8. Now, let for each pole of the inverter, if the voltage level minus VDC by 2 is indicated by minus sign, it means the bottom switch is on, and VDC by 2 is indicated by plus sign, which means above switch is on, means for leg A, if S1 is on, I will represent plus sign, and if S4 is on, I will represent minus sign, okay. So using these symbols for all the three legs, we can represent switching as plus minus minus, plus plus minus, plus minus plus minus, minus plus plus, minus minus plus, plus minus plus, minus minus minus, or plus plus plus. These are 8 switching states, and for every switching state, the sign indicated in this box represent the state of switching of inverter pole A, B, C respectively. The voltage space vector corresponding to these 8 switching states of the 2 voltage inverter are defined as V1, V2, V3, V4, V5, V7, V6, V7 and V8 respectively, okay. So now if we talk about the phasor structure, we use all these equations to make phasor, okay. Now the phasor will look like this, okay, and it is a custom to place alpha axis along A phase axis of the induction motor. Now the the triangular sector of the inverter voltage space phasor structure are indicated by encircled number 1 to 6, as it is clear from the figure, okay. In case of voltage vectors V7 and V8, all the three poles of the inverter are connected to the same DC bus, okay. which is effectively shorting the load and resulting no transfer of power between DC link and the load. Hence, V7 and V8 are known as zero voltage vectors and can be represented by V0. In case of each of the remaining 6 vectors, power get transferred between DC link and the load. Therefore, these voltage vectors are known as active voltage vectors. Now, if we talk about N level or general N level inverter, the number of switching states, let T, can be determined by T is equals to N to the power 3. Okay, and the number of voltage vectors, let, can be determined by equation 3 is equals k is equals to 3 and n minus 1 plus 1. Okay, now let me show you how a 3-level inverters voltage space phasor structure look like. This is voltage space phasor structure for 3-level inverter. Okay, and if we talk about 5-level, this is 5-level inverter. Okay, now the poles of level 0 is indicated by 0 in switching states. However, in 3 level it is not denoted by 0. Okay, now the pole voltage levels minus VDC by 2, VDC by 4, VDC by 2, 0 and minus VDC by 4 are represented by different numbers, which are minus 2, minus 1, 0, 1, 2. Okay, in the switching states, for the sake of clarity, for 5-level inverter. Okay, so on screen you can see there are number written in form of minus 1, 0, 1, 1, 0, minus 1. Yeah, these are switching states for 5-level inverter. Now, it is to be noted that the voltage vectors V7 and V8 effectively generate the same voltage vector location. Hence, the switching states minus 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 and plus plus plates each generates the zero voltage vector and are known as redundant switching states for zero voltage vector V0. Similarly, the switching states which generates the same inverter voltage vectors are considered as redundant switching states for that vector or that voltage vector. Okay, in the voltage space phasor structure, the center 0 inverter vector has multiplicity or multiple switching state or redundant switching states for, okay, for n level it will be n, and for 2 level it's 2. Okay, as evident from the figure you can see on the screen, and let me show you. See here, in 2 level it is having 2 redundancy, in 3 level it is having 3 redundancy, 0, minus minus minus, plus plus plus, and in 5 level it is having 5, 1, 2, 3, 4, 5. Okay, so the multiplicity of switching states for the inverter vectors goes on reducing as one moves toward the outer inverter voltage vector location of the voltage space phasor structure, and the outermost inverter voltage do not have any redundancy. In the PWM switching, the 3 nearest or adjacent inverter vectors at the edge of the triangular sectors in which the tip of the reference voltage vector, which is Vs, is lying, are selected for inverter switching, which means for the switching purpose here in this figure, in this 2-level inverter, as Vs is in first triangular sector, then V1 and V2 will be used for switching, and sorry, V7 also. So V1, V2 and V0 will be used for switching purpose only, and other will not be switched. And when it is in second triangular sector V2, V3 and V0 will be switched. Now the distance between the reference voltage vector and the nearest inverter voltage vector directly determines the harmonic content of the output voltage waveform. Okay. Now seen, as it is seen from the figure, the inverter voltage vector are placed very much closer to each other for higher level inverter configuration. Okay, which results in the reduced harmonic content of the output voltage, and the current waveform are more sinusoidal or having lower THD. Okay, so in this lecture we have seen the phasor and how to switch voltage and between the different voltage states, switching states, and their different level of multi-level inverters. Okay, I hope you understand different type of or different levels of multi-level inverter and their phasor from this video lecture. Thank you.